вітаю. Раді вас знову бачити на зустрічах нашої дискусійної платформи «Наука для відновлення та сталого розвитку». Сьогодні для нас зробить презентацію доктор Михайло Zhizhin. Він є доктором філософії з обчислювальної сейсмології та розпізнавання образів. Він є науковим співробітником Інституту Пейна, професор Університету Колорадо School of Mines. Ми раді вас бачити, доктор Zhizhin. Welcome, Dr. Zhizhin, on our platform. Please, you can start with your presentation.
Hello, good morning, good evening. So my name is Mikhail Zhizhin. I'm a research associate at the Payne Institute, Earth Observation Group, Payne Institute, Colorado School of Mines in Golden, Colorado. And I will discuss today or present the way how we can use remote sensing for tracking changes in environment and social-economic situation due to the conflicts. So my group, or the group I belong to, is relatively small. We are just 4 people. Our director is Chris Selvich. He's a very famous nighttime light researcher with more than 30 years of career in this field. I have joined the group in 2012. Then the new satellite was launched. It's called GPS, Joint Satellite Polar Orbiting Satellite Program. And the first satellite was launched 1st of April 2012. Started to downlink data April 1st, 2012, and I arrived in Colorado the same day. So I'm working from the beginning with this data. And we have several products related to this satellite program. All of them are nighttime. So we study phenomena on the Earth's surface at nighttime. The lights and heat sources. So the products are maps of lights from cities and human settlements. We have a boat detector at night, which will just look for the spikes in the ocean, which we interpret as lights from fishing boats. And in infrared, we study gas flares is our main interest, and also fires, which is a byproduct or sometimes even noise for us. So the main purpose of this satellite program is meteorology. And on board of these satellites, we have visible infrared imaging radiometer suite, VIRS, which is designed to track clouds and some atmospheric events. But during nighttime, it is so sensitive that it can see lights from mainly human settlements. And this is an example of city lights from Manila, which were acquired on March 23rd, 2016. And you can see patches of clouds here, some region on the upper right, in the upper right corner, upper left. Some lights are blurry because of the cloud cover, but we can collect this from periodical observations and clean for the noise, accumulate clear data, and make the products. This is an example of infrared image from the same satellite. It has several infrared bands, and you can clearly see large fires. And also, this is an example of gas flares in Bakken. This is a North Dakota oil field. And daytime, it's just the signal of from terrain, from sunlight reflected by the surface. But at night, when you have no sun, these pinpoints are the signatures of gas flares. This is the flagship product from our group, and these are the annual light time maps. We make them every year from 2012 till now. And you can see the development of the settlements in India, where you, from year to year, you have more and more lights and population growing. And so this was the first chain of products, annual and monthly maps of the nighttime light. Also, it is possible to make color composites, which are the pre-layer color image, where you can display the changes during some events like blackouts. Well, we use colors for original lights in green, for the current lights after the event in red, and blue denotes clouds. So these color composites can enhance or present visually changes related to blackout or light dimming. Originally, this was done by hand, so it's kind of hard. You have to stretch the images, play with them on, say, Photoshop to get it more visible. And one more product which we are pursuing with the nighttime lights is radiance profiles. So this profile was made in 2022, I guess, and you can see that we, for a given location, we make time series of the radiances in visible band. So take pixel and just display it as a scatter plot with the timestamp. And this is a plot from location in Kabul, where there is a US embassy, and you see an obvious dip in brightness after the US withdrawal from Afghanistan in August 21. So the second line of the products we have is Veer's Nightfire, and this is related to the infrared. As I already have shown, is this is the signal in shortwave infrared from gas flares in Texas, and this is a thermal infrared channel which shows you the background temperature of the Earth surface and clouds, but the signal from flares is missing. So at night, satellites have nine infrared channels: M7, M8, M10, 11, 12, 13, 14, 15, 16, starting from visible near infrared, going to this M8, M10, M11 are the channels with shortwave infrared. M12 and 13 are long mid-wave infrared, and 14, 15, 16 long wave. To understand how we use it, I have plotted the spectral windows for each channel, overlaid the plane curve from two hot black bodies. One is 1800 K and another is 800 K, reflecting or representing the gas flare temperature and forest fire. You can see that for a gas flare, shortwave infrared channels M10 and M11 are the most responsive, sensitive, or they have the more signal. And for the forest fire, because of the shift in the Planck curve maximum, we have more signal in M12, M13 in mid-wave infrared. And these 4 channels are used as a detection channels for the inverse night fire to detect heat sources. Based on this thermodynamics, we can recover 2 parts of the heat source. One is the Planck curve from the subpixel fire or flare on the image, and the second part is the background, thermal background from the surrounding clouds or land or water. So using nonlinear unmixing, we can estimate temperature, area, radiative heat from the subpixel heat source. We collect this data nightly. Currently, we have 3 satellites, SOMI and PP, launched in November 2011. NOAA 20, which was launched in November 2017, and NOAA 21, which was launched in November 22. So the SNPP has a time span 13 years. NOAA 20 has a time span from 2018 to 2025, and NOAA 21 from 23 to 25. We have a paper on sensitivity of this method. So it depends on temperature of the heat source. Hotter is the source, more sensitive, and it's more probable that we will detect it. And on the y-axis, we have a source area. So if it's a gas flare, we can detect less than a square meter. Then the temperature cools down. Then we have to, well, for a forest fire, it should be something like 10 square meters to be detected. Persistent emitters. So we can collect all our detections so in a raster, make water shading, and kind of separate emitters which are repetitively observed every night. Then playing with this imagery and using some clustering technique, we call it super resolution, we can localize them with very high precision. Say the satellite pixel is about 1 kilometer, but we can separate flare stacks, say 400 meters apart. And the contours around the flare stacks, we call them bubbles, they indicate the regions of influence. If a pixel center from a new image falls into this bubble, we assign the radiance to this emitter attributed. Then we collect these profiles for all the persistent sources and make some catalogs based on the temperature and imagery invisible at night, at daytime from Google Earth or whatever. They can attribute them as upstream, downstream flares, refineries, steel mills, kilns, cement kilns, and so on. And they have different temperature signatures. So the hottest are upstream flares, the coolest are volcanoes. We can see landfills and so on. For the project with the wall bank, we calibrate upstream flares in units of flare gas, methane, and we are reporting the amount of flared gas by country, by flare, annual numbers and monthly numbers every year. So World Bank Group for Methane Reduction will publish a report This month, I think they will publish it for 24, where they, based on our observations, they report how much is flared by all oil and gas countries. As you can see from this graph, the main flarers are Russia, Iraq, Iran, United States, Algeria, and Venezuela. For each persistent emitter, we have profiles. So this is a profile of one of the gas flare in Syria, where you clearly can see the gap due to the civil war. So upper one is the signal in the most sensitive channel M10. The middle plot is the temperature of the emitter, and you see it's steady about 1800 K. These stripes at the bottom, they indicate our ability to detect. So the white one is just when flare was not detected, we report by cloud state. Red segment is cloudy, blue segment is clear. And this small stripe is when we can detect a flare just in one channel, so we cannot fit temperature. It was too small. And the bottom one is flared gas volume. After the calibration, we can see how much this flare is burning in millions of cubic meters per day. Another example is a steel mill in Mariupol. We don't report flare gas volume because it's in our source, it's just kilns, but we can definitely see that it was when it ceased operation in March 2022. Now transient IR emitters. So I would say what the scale of the conflicts in the last few years is so significant that it requires some additional, I would say, research and new methodology to be applied to study this. So in a point-wise, we have just a few cases, observed few cases or studied when you can trace the signature of the accident or some conflict-related event using this infrared detections. So this is a report on the explosion in Russian arsenal, which happened a month ago. I think I have a movie to see how we can how this event develops during the night. So we have about 4 satellite passes. These squares or rectangles, they represent the footprint of a single pixel in infrared image. And the opacity of the rectangle is proportional to the radiative heat. So less transparent, more heat is radiated at this place. So you see how it propagates through the night. And you can compare it with the aftermath. This is a daytime image after the explosion. So I think we are picking relatively well, geolocating the main destruction. Same story with chemical explosion in Iran, which happened on April 26. So this is a port. And again, the aftermath next day image from high resolution satellite, and this is a movie. So you can see with infrared quite well the location and scale of this event. Going large scale, we can take a region and plot all the VNF detections and also color it, animate by color the propagation of fires. This is example from southern Colorado. On the left, you have a density map of fires overlaid with some Indian reservation boundaries, which we used for another study. And on the right, you see the locations of the heat sources, colored by red if it's above 1,400 K and blue when it's below 1,400. So we interpret it as the fires and industrial sites and flares. And this is another view on this thing, histogram of the temperatures of the detections and time plot, where you definitely clearly see the bottom stripe as fires and upper as flaring activity in the region. And you can see by the radiative heat, accumulated radiative heat, the largest fire events in the region. So if to look at the conflict, the picture changes. So on one hand, you see you can trace the by density maps the main regions where the military activity do happen, and remote regions where are effects of the drone attacks or whatever. In time, the picture is more mixed. So we don't have this bipolar or bimodal distribution anymore. So it's we have a small bump here from flares, but mainly most of all the temperatures are possible. And you can see the radiative heat as a proxy of the development. So this is the beginning of the Kursk operation. So radiative heat is much more intense here. And for the similar animation of the temperature and time of the events, I use three colors now. The hottest are red. These are gas flares in Black Sea and then Belarus. The green are coolest, so these are most probably forest fires, and the magenta are those around 1000 K, which are most probably related to the military conflict. So I should have an animation to try to see it live. Give me a second. Yeah, so this is the density map. And the whole Kursk area is covered with the detections. If we do the animation, you can see how it propagates with time. Let's start from the beginning of August 24, just from the beginning. You can zoom in Kursk. So this is an insight which we can get from the infrared part of satellite imagery. Let's look at the nighttime lights. So this part of the work was supported by NASA research grant, which last year. So within this activity, we have developed I call it data cube. We collected all the pixels from Suomi and PP satellite, the first one, in the study region, including Ukraine, Balkan countries, Poland, southern Russia, and Belarus. And based on this data cube, we could do two things. We can make snapshots in space, and we can take temporal profiles in time. Because the area is so large, we have collected data only for the pixels which were lit before the conflict, before the war. So the first thing for data mining, we have made a profiling tool. So these are the plots not from Ukraine. One is from Gaza on the left, another is from Sudan. But you can see that in both cases, the conflict signatures are quite apparent. See here, interesting, we have this blue part which is cloudy, upper part which is clear, and I would say that in Sudan, cloud detector developed by NOAA works quite well. Say in Gaza, this bottom part reddish, it should not be red, I would say. It's just a kind of malfunctioning of the cloud detector. This is a known issue. In some places, clouds which obscure visible light are not perfectly detected, and we are working on this. Possibly we can get it interactive. So let's try this for Gaza. So we move the cursor, and what is it? Say in Syria. Let's try to get profile. Yeah. So no change. Let's see in this place what is happening. Yeah, the lights are decreasing. And if we go to Gaza, let's see what is happening here. Yeah, obviously, after the beginning of this war in Gaza, signal got lost, I would say. Egypt. So same thing we have for Sudan. That's capital. If we go to some remote places, I think the picture will be opposite. So people are moving outside from the capital just to save their lives. The next step is to segment the time series. So we have a machine learning algorithm to track a trend in the brightness and separate segments. These are pre-war time series, and you can see the seasonal changes. So snow, no snow. After the war began, you see this sine wave reflection of lunar cycle, but the presence of lunar cycle in this time series indicates that the lights are very dim. So we can report the mean radiance for each segment and the dates of change. This is an example of segmentation for different cities, and this line is propagating all of them, for all of them, so it's the beginning of the war. We have tried to describe the changes visually. So the scale of the changes, radius of the circle, and the under every circle there is a time series which can be plotted. Let's try. I should have it working. So Mariupol, Sumy, and so on. So before the war, you see a strong signal from snow in winters, and then there is basically no light as the war began. Another way to look at this is to introduce a dimming index. So it's just the ratio between the mean radiance in this trends before and after the war began, and to do it for every pixel on 15 arcsecond grid. This is a region of study we apply this technique, have applied this technique. The gray is nighttime lights map before the war in 2021. And we had a similar tool to profile and segment the time series. Let's try it. I think it's here. Yeah. So compared to these examples in Gaza and Sudan, here we have more analysis. We extract time series and we look for the change. And this is the dimming. So the ratio with the signal year before, this green line. And with a special customized color palette to show the percentage of dimming. So red is the lights are less bright, blue is they are brighter, white no change. We can get an animation. So this is a map of all the known city lights before the war, related to previous year radiance, and this is after the war began. So I should have this movie. We can try it. I'll try to run. So you see the date at the bottom, starting from January 1st, 2022, approaching the beginning of the date of the beginning of conflict, which is 24 February. And you see it's rapidly dimming all the country. Here it could be some atmospheric things like dense cloud cover in Poland. But the change within the country stays for a long time. And to conclude the presentation, so with Vir's Nightfire with infrared signal, we can pinpoint significant events during the night and just animate how it develops, because we have multiple satellite overpasses per night. We can draw temporal profiles and see the changes in industrial activity. Density map for large areas can vividly illustrate the progression and spatial dynamics of military campaign. And nighttime light observations with profiles offer critical insight in economy, infrastructure, population. Using this dimming light ratio, we can somehow quantitatively assess the change. But what is lacking here, it's a relation with parameters like population density or gross regional product. This has to be studied more. Thank you. That concludes my presentation.
Thank you very much for your presentation. Sorry again for this some prankers performance. Now I think we can start our discussion part. So please, people who have questions to discuss, raise your hands. You'll be unmuted, and you can like have a live discussion with our speaker. Yes, Andrei Shelostov, please, your question.
Да, доброго дня, шановні колеги. Я мав проблеми зі з'єднанням. Дякую за прекрасну презентацію. Я ж можу на українській, да, Леонід?
Так. Якщо що, я перекладаю.
У мене є два питання. Одне, в принципі, технологічне. От з одного точки зору тут видно, що це фундаментальне дослідження, використання різних різноманітних даних для розв'язання таких достатньо складних задач. З іншої точки зору згадуються інтерактивні засоби. От у мене питання: наскільки це готово для використання, наскільки воно от має вигляд готового рішення на рівні вхідних даних, їх підготовки і так далі. Це перше питання. І друге питання: оскільки згадувався проєкт Світового банку, то такі організації, як правило, зацікавлені в отриманні не просто оцінки якихось параметрів на основі супутникової або геопросторової інформації, а вже в термінах або економічної діяльності, або перспектив розвитку, або розміру пошкоджень заданого типу, там в термінах площ, культур, об'єктів і так далі. Тобто, наскільки ця технологія або підхід дозволяє перейти до оцінки таких показників. Дякую.
So, Andrei is asking, first question is more technical. What is the readiness level of the products and technologies that you showed? Like you mentioned, there's DataCube, either possible to share some resources that already publicly available or gonna be publicly available soon. And second question is, you mentioned that like a lot of stuff was made for World Bank, but World Bank and other organizations are really interested not like only on remote sensing indicators, but how to go from remote sensing indicators to the measurements of economical development, economical indicators, and how they are measurable based on remote sensing data.
I will start to answer from the second question because I think it's more easy to answer. Just a sec, I'll get this plot. So this is already intermediate product. It's not remote sensed one. We report flared gas volumes. These are the entities which can be measured technologically, and not just you can compare it with the reports by the oil and gas companies on one hand. Never you can just the price of the gas. You can interpret it in money value, and you can see the lost opportunities. Imagine you put a generator near this gas flare. You can get the electric power. You can crypto mine or whatever. So this is already economic interpretation of what we see. To answer about the readiness, I think for the part of the conflict monitoring, I'm showing the cutting edge state. So this is a research project, and we really do not have any customer who has an interest to have it operationally yet.
But you're planning to provide open access data sharing or access to the DataCube analysis ready data?
Well, the project with NASA has ended in July last year. And we are, I didn't mention, we are a soft money group. So we are not paid by students. We are paid by our customers. So we have a data subscription when we send alerts for bow detection or fire detection, or we provide the temporal profiles for the customers of consulting companies, the World Bank, think tanks, and this is how we provide our we do exist. It's our support. So I don't see that we will go open source with this first, and second, provided we will have some source of the support, we can develop this further.
Thank you. I have a small question. So in your study, like nightlight studies for Ukraine are very complicated right now because we have blackout, so we have rapid changes not only on like monthly or yearly basis, but daily basis. and how to like incorporate the fluctuations in the nightlight intensity in the days with blackouts and days without blackouts into research to get more valid interpretations.
Just a sec. So you see, well, there is a mixture. We have different signals like city lights. They are obscured by clouds. We have a lunar cycle. It's apparent in Kharkiv. And so the question is what we are looking for. If we are looking for the long-term trends which reflect state of the city under the conflict, recovery, or which can be translated into the number of population, people living there, or some industrial activities, or even policy, how you hide the lights, just to not to attract drones or whatever. This is one thing. And another is just a snapshot during one night. For example, the recent blackout in Spain. They were lucky to get power back before our satellites came at night. So we do not see much. But we can try to extract some short-term signal or signatures from blackouts, which is not easy. First, because you explained that there are natural fluctuations, there are some even satellite view angle will influence the radiance. And to automatize this, it's another task. So I wouldn't say what we have this technology now. So long-term trends, week, month, doable. Very short changes, questionable. And more insight is from infrared, because this is a strong part. It's less fluctuating. If it's burning, then it's burning.
Thank you very much. We have a question from Andrei Koloti. Ask to unmute. Andrei, you can ask question.
Так, теж українською. Доброго дня, дякую за цікаву презентацію. От трохи в продовження питання, яке вже було, а чи розглядалися якісь зв'язки економічного розвитку тих чи інших територій та Nightlights?
Related question to the previous ones. Did you like study the dependencies between economical development of affected territories with changes in nightlights?
Short, yes. This conflict has a long story, and the first phase in 2014. We just tried to get summer flights, monthly summer flights in what it was, Belgrade, Kharkiv, Kiev, and then in parallel there was a German report on the economy in these regions affected by the beginning of the conflict. And I think that the ratio in regional gross product and ratio in nighttime lights radiances monthly, they just match percent to percent. We did not study this in detail after the 24th of February 22, because well, data is I would say it's more difficult to get the data, and the scale is much larger. So what I can say, that if you look at steel mill signal, heat signature from steel mills, apparently you can see that the industry is just ceasing. This is visible. This study was just piloted, no more.
Thank you. Any more questions? Okay, I think if there's no questions, we can conclude our meeting. Thank you very much, Dr. Zhizhin, for your amazing presentation. Thank you, participants, for participating. We will process the video and we'll release it soon. So keep in touch for our discussion platform meetings, and hope to see you again.
Yes.
Everybody, thank you.
Yeah. Stay safe. Bye.
Thank you. Thank you. Bye.